Welcome to Talking HealthTech. My name is Peter Birch. Today on the show, I was thinking, given that we've spoken to people from pretty much around the entire world here on the Talking HealthTech podcast, I was wondering where else can we go to bring some new insights? And so why not think a little bit further? So today we're talking about healthcare in space. So in this episode, I speak to a number of healthcare professionals in Australia and New Zealand who've dedicated their life to what healthcare looks like in space. Today on the show, you'll hear from Dr Vienna Tran. She's a GP registrar and space medicine researcher and formerly at the Australian Space Agency in applied space medicine and life sciences. We talk about how space medicine is essentially extreme rural healthcare because there's zero backups and no support. We talk about the impact that microgravity and radiation has on the human body and what we can learn from space and apply that into remote and preventative care and resources for us here on Earth. Then I speak to Professor Gordon Cable. He's a professor of space medicine, co-founder and head of flight medicine for human aerospace, and he's a fellow for the Australian College of Aerospace Medicine. We talk about how human health is the major limiting factor of long-duration space missions. We reflect on how a lot of the technology we see today in healthcare has originally come from healthcare in space. And we touch on AI, robotics, and on-demand manufacturing, how important they'll be for off-planet delivery. Then I speak to Dr. Lisa Brown. She's a trauma surgeon and lead for the New Zealand Space Health Research Network and a space medicine researcher at University of Melbourne. We talk more about microgravity and how that impacts organs and how they behave and heal and respond to intervention. Talk about some different studies that they've done and the research that's happening in relation to space and what the future may hold. And hopefully this episode gets you thinking about innovation and doing things differently, because maybe some of the trickiest challenges we have here on Earth in healthcare are solutions that are out of this world. Collaboration starts with a conversation, Team HealthTech. Let's make it happen.
I'm Vienna Tran. I'm a GP anaesthetics registrar in Australia, and I'm a space medicine hopeful.
Space medicine hopeful, love that. Tell me a little bit more about what that means.
I have been in love with space ever since I was about 5 years old. My dad took me to an observatory about half an hour north of my house, and through the telescope that they showed us, we saw the moon. We saw where the night met the day on the moon. We saw craters, stars, planets, moons around the planets. And from then I was in love with the unknown. I was fascinated by what we didn't know and the things out there that were beyond Earth. So he bought me a lot of astronomy books. He showed me astronomy documentaries, and he wanted me to be a science and maths person. I ended up being that person, but with a particular affinity for space. So unsurprisingly, I wanted to be an astrophysicist when I was in school, but I ended up choosing medicine because I wanted job security, and that's something that you can get with healthcare jobs here in Australia. So I thought I was kind of locked into medicine, and somehow fate would have it that the International Astronautical Congress came to Adelaide in my third year of university. I attended it as an orchestra player for the opening ceremony, then decided I'd attend as a student just to have a look around. Yep. Discovered the space medicine technical session, realized that space medicine exists, and I was on a direct trajectory towards a space medicine career. It gave me the boost that I needed to finish medicine and find my purpose, my calling, if you will.
Yeah.
So, yeah, since then I've been participating in conferences and school talks and anything and everything that's space, and sharing my love of space health with the world.
Absolutely love that. And, I feel like that even that introduction can provide some interest, maybe inspiration to clinicians or anyone that thinks about a career trajectory that might otherwise feel somewhat unattainable. And I guess to go from 0 to 100, or for want of a better terms, could be a little bit tricky. But I guess when I think in healthcare, there's probably a few tangents or parallels in other parts of healthcare that might help kind of build you up to that space medicine, not end goal, but I guess direction that you're going. Like, where are the parallels between like what we do in healthcare now to doing the same thing but in space.
There's a lot of parallels. If you think about it, space is rural. And so when you frame it in that way, then whatever we do to help people in rural health and remote communities especially, but in all of healthcare too, can actually be applied to space. After all, we apply Earth medicine to keep our astronauts healthy. We have been doing that ever since we sent the first person up to space. All we know about health comes from what we know on Earth. But in resource limited areas, that's where the challenges come in that we have to learn to deal with on Earth, and we can apply that knowledge. So, for example, the way we communicate in rural communities. So depending on how far away from a city you are, you will need to ring somebody for help. So that can be over the phone, verbally, or over video conference. In my first year working, I started working in a regional hospital, and we don't have neurologists to help diagnose stroke. So we use the telestroke service. It's a service that exists in South Australia for regional hospitals, and we video call in, and that stroke consultant will look at the patient and help us do the examination to determine whether the patient needs further imaging. And I can think of that as we are getting help over a distance. That person doesn't need to physically be here to help us with that person's condition. So in space, it's 400 kilometers from here to low Earth orbit at the shortest. So they regularly do private medical conferences once a week to the astronauts on the space station. A doctor has a confidential conversation with that person. They have actually tried doing a hologram of a doctor or multiple medical professionals to beam up to the ISS to make it a bit more realistic. So that already exists. I think they do fortnightly psychiatric conferences as well. So telemedicine already exists in space too. And when we go further out to space, then the delay is going to be longer. So there's going to be more of a need for autonomy, more of a need for onboard decision making, and a greater capability to be able to deal with that delay so that packages of information can travel the 2 minutes to 22 minutes that it takes to get to Mars.
And I think about here in Australia, I've always been a big advocate and supporter and hopeful, at least, that, given the geographical breadth of the country and the need, we should be really good at rural and remote medicine and all the kind of services that wrap around it. And generally we are, and always room for improvement and stuff. How do you kind of see Australia's placement when it comes to being able to contribute when it comes to space medicine?
Yeah, so speaking of how rural medicine helps space, another thing I wanted to mention was the resource utilization. So when you go far distances, you need to make things smaller, cheaper, and easier to transport. And we do that very well with our small medical devices in Australia. Things like the what we call the VBG machine, like an iStat. You can take someone's blood and then just put it on a cartridge, put it in. It takes 10 seconds, and then it analyzes a whole bunch of really important electrolytes, for example. And they have trialed that in the space station as well with blood, saliva, and urine. Lab testing, they are still working on that. Imaging, they use an ultrasound, something that at night in an ED in a rural hospital, you may only have access to a point of care ultrasound. So the people who are skilled in using ultrasound are also happen to be the types of people that they'd be looking for as space doctors. In Australia, we have a large geographical area. We've got, expanses of empty land where small rural communities are dotted around the place. And we have a fantastic healthcare delivery system across that vast area. An example being the Royal Flying Doctor Service, the planes with the famous red bellies and the blue strip, the ones that you see ads for all the time on TV. They're a huge charity, very worthwhile donating to them. They have their national office and the state offices as well. And every 2 minutes, somebody needs the RFDS, whether it's via telehealth or via retrieval. Every 2 minutes. So we're really experienced in this area. We know what to take with us on the plane, who to take, what information to get, and deliver of ultimately the right care to the right person in the right time frame. Australia happens to be also very good at biomedicine and the health sciences. It's probably a result of being a Western country, but not actually in the Western Hemisphere. It's had room and agility to grow its own capabilities in its own way without perhaps the red tape of some of the other bigger Western countries. And we have a really smart, creative people here. We have a can-do, have-a-go attitude, and it's a great breeding ground for startups and ideas for how to look after people's health in better ways. So that has allowed people to research really innovative solutions to healthcare problems, and really lead the way in a lot of fields, including, for example, the University of Adelaide looking at how we shield medications by changing the binding ingredients or the excipients in, say, ibuprofen to take to space so it lasts longer. Another person who happens to be from the University of Adelaide, where I graduated, is looking at plants for space. It's a national consortium looking at how we're going to grow plants safely in space, which plants to grow, and what benefits they will give us. That will also, by the way, enable good food security and safety back on Earth. So space is for Earth, and space is for Earth, and Earth is for space. It's a real cyclical benefit, which is really, really exciting to me.
Yeah, as I go down this rabbit hole of space, and just, super valid point you bring up around the broader kind of biotech side and the, moving into the ag space, it by innovating in an environment that is not our own, it provides new constraints that then breed creativity, that then bring ideas back that we would not otherwise have, we may not otherwise have encountered. So that's super cool. It makes me think, though, is the pursuit of, exploring innovations in space more beneficial from a research and development side, or do you see that, this is stuff we really should be doing because it will become, space travel will become more accessible to a broader public at some point in time?
I think it's both. I think if you were to look at the dollar value of every dollar that is spent in space, you actually get greater than a dollar value back in return. So that can be via research and development applications. Currently, I believe in the world, out of all the different benefits that we get back on Earth, space applications is the most. So every satellite that is launched into low, middle, or geo orbit, it takes pictures of the Earth that are valuable for us to know here on Earth for weather prediction, military operations, climate monitoring, that sort of thing. So when it benefits a great number of people on Earth, I think that's fantastic. I think that's where you can sell the idea that space travel is fantastic. Right now, in its early stages, people actually going to space, that's going to be a much slower growth. It's going to obviously start with the people who have money and the ideas and get chosen for it. But that is the same with any other innovation. Back 100 years ago when aviation started, not everybody could afford to fly a plane. Not every company could afford to build planes at a large scale. Only the really creative people who were in the right place at the right time and had the right privileges were able to do that. So it's going to grow more and more and more significantly, and it's going to become more commonplace with time. But if you want to sell the idea at first, and if you want to show the public that space is beneficial for all, then the research development benefits and how it benefits human health are the way to do that and communicate that idea. And the more public support it, the more we realize that space is going to be here to stay.
From a humans going into space perspective, I understand a bunch of stuff happens to your body that doesn't happen back on Earth. What are the main things that happen to a human body the further it goes up into space?
So you can split these into a few main hazards. The most obvious one is microgravity. The other ones, though, are radiation, distance, isolation, and extreme environments. In microgravity, you can see that straight away. As soon as, the SpaceX Dragon capsule hits microgravity, then Earthy, the little plush Earth toy, starts to float in amongst the 4 astronauts that are sitting there. And that's the indicator. That's the canary in the coal mine that tells you we are in microgravity now. This is not a trick. It's not an illusion. So microgravity has acute changes. It causes acute changes to the human body, right? So our body is a big sack of water. So we are 70% water, and we are a flexible being. Our skin and our integumentary system is not fixed. And so the fluid shifts from the legs to the head and the chest. When the fluid does that, then very clearly and visually, we get skinny legs, we get chicken legs, and a puffy face. That causes congestion. That causes headaches, possibly nausea. And that can impede mission objectives if you try to give tasks to people too early. So there needs to be some time for adjustment. Your heart your whole body is used to evolving in a 1G environment. So everything is shaped a certain way. When you go to space, your heart becomes a spherical shape. It also, because all that fluid, including blood, stays in the upper extremities where there's a lot of vital organs and brain, the heart doesn't need to work as hard because it's supplying that nicely. So your heart actually gets smaller. It atrophies. Simultaneously, so do your muscles and bones. Your muscles and bones and your MSK system, musculoskeletal system, work on the principle that if you don't use it, you lose it. So if there's less neuromuscular and axial loading on the bones, for example, it doesn't feel like it needs to hold on to that calcium. So it leaches out the calcium. Calcium goes into the blood. Side note, calcium in the blood gets filtered through the kidneys and puts you at higher risk of kidney stones, which has happened in space before. Muscle atrophy is fine while you're in zero gravity because you can be floating around, but as soon as you land back on a gravity body like the Earth, Moon, or Mars, then weakness occurs, fatigue, risk of injury because you don't have that strength that you once had. And that's why astronauts have to exercise up to 2 hours a day, resistance and cardiovascular training, to maintain that. And even with those countermeasures, they still experience losses that could be considered dangerous. Radiation is an interesting one. It affects the cells, the food, the electronics, especially when you go beyond the Van Allen belts. Now, only 24 people have been beyond the Van Allen belts, which is really the result of the Earth's magnetosphere protecting the Earth from the harmful radiation that has hit other planets and caused life not to be able to exist. So we don't have much data about what happens to humans beyond the Van Allen belts. Distance, extreme environments, and isolation. These are all kind of related, and it's to do with the fact that we are so far away from help. We are confined, and so bugs don't leave us. They stay in the space station. Waste doesn't leave us. And psychological effects are profound. So that's why they must do good psychological selection so that they make sure that the right people with the right stuff who are resilient can go to space rather than the average Joe. So lots and lots. This could be an entire episode if you wanted it to.
100%. I would really enjoy that, but I've already committed a bunch of short conversations. I forgot I was doing an interview. Lastly for now, for those clinicians who are listening to this episode and think they would want to explore more in contributing towards space medicine or even just learning about it, do you have any recommendations?
Talk to people. The space medicine community, especially in Australia, is small and it's tight-knit. I've gotten to where I am because I talked to people. I networked. I attended as many conferences as I could. I gave up a lot of time to do that. I wrote small papers and literature reviews so that I could share something with others and that I could also improve my own knowledge. I read textbooks. I did school talks because if you can teach it, it means you know it. and connect with the groups. So here in Australia, we have the Australasian Society of Aerospace Medicine, or ASAM. You can become a member, you can go to their conference, and you can go to their Humans in Space course, which happens every single year. And it's a short course, which is a great introduction to aerospace medicine. The American version is called ASMA, or the Aerospace Medicine Association. I am yet to go to one of those conferences, but they are huge. They incorporate aviation, occupational, military, and aerospace medicine, and the best of the best in aerospace medicine go to that conference. So you've got to mix with the best. And if you want to contribute from a research point of view, then in Australia, our space agency resides in Adelaide. So you can contact them and see where you could fit in. You could go to one of our space forums and talk to people about how your area of interest or research could help space. It's all about having that conversation, because it's such a new field, especially in our humble country, that there's no formalized process for submitting, your interest or your research. So just have the conversation, and beautiful things can come out of that, I promise.
Hi, Peter. Thanks for inviting me on the podcast. Professor Gordon Cable's my name. I'm formerly a professor in the practice of space medicine at ANU, now with an honorary title, but my work is predominantly at the moment involved with my private company, Human Aerospace, which has been looking at microgravity countermeasure strategies and developing those over the last few years with grants very kindly through the Australian Space Agency. My background is medicine. I graduated medicine from the University of Sydney quite some time ago now, but decided that aerospace medicine was my passion and what I wanted to pursue as a career. So I started to, apart from learning to fly, doing some study in that, and ended up working for the Air Force for 26 years, doing aerospace medicine training. In the last 10 years, really developing quite a subspecialty interest in space, and that's why I'm here, because I've been involved in some university courses. I've been involved in working for the Space Agency for a brief period, helping them develop a plan where they want to take space life sciences over the next 10 years. And it really developed, a really deep interest in how Australia can contribute to ongoing potential human missions into deep space later on.
Amazing. When you say space and human life sciences, like what does that mean? Unpack that a little bit more for me.
All right, so life sciences in space, I guess it involves humans actually traveling in space and the health and welfare, safety of humans in really extreme environments, and space is an extreme environment. But it's also about life sciences in so many other ways. It's about doing research, health research, life sciences research in space, looking at how we can develop technologies or drugs or techniques that help astronauts, that can help us, or that we actually use space as a laboratory to specifically use the space environment to develop technologies and healthcare strategies that are beneficial back on Earth. So there's a number of ways you can look at it. Life is also involving plant life, and at the moment, for example, there is a Plants for Space CRC that's been established, looking at how developing plants for a spaceborne environment, the sturdiness, the ruggedness of plants to survive in space. Imagine how that would help remote and austere and disadvantaged communities on Earth to grow crops and to grow food in really austere desert-like climate. So there's a range of aspects of life sciences. My specific interest is medicine, so I'm really interested in how you protect humans in the space environment, and that's essentially what my company Human Aerospace has been looking at over the last sort of 7 years or so.
Amazing. And like the purpose of that, because someone who, like myself, who's not deeply entrenched in the world of space travel, I might look at that and think, that sounds interesting to do. But in terms of the day-to-day practicality of that, I'm not sure. Like, I've got a few flights booked, but they're all within this planet. And I don't immediately plan to travel beyond any certain kind of height. Like, what's the practical and obviously there's funding and there's interest and there's all of that in Australia and globally too. I want to come back to Australia in a moment, but why? What's the purpose of all of this?
I'm interpreting your question to mean, what are the challenges in space that we have to overcome? The purpose of space medicine, is that what you kind of asked?
Sure, yeah, absolutely.
I guess,
it's important,
the challenges, there's so many. Space is an environment unlike anything that we really see on Earth, and I think the most obvious problem of going to space, whether you're talking low Earth orbit on the International Space Station or deeper into space, is altered gravity. I mean, we have to deal with microgravity, either on orbit on the space station or on a vehicle heading to the moon or Mars, and floating around weightless does a whole bunch of stuff to your physiology. Everything from bones and muscles to the cardiovascular system, the balance system. It is all profoundly affected, and we need to come up with ways to try and preserve the normal human physiology reflexes as best we can. Humans adapt really well, to that, and the human body, its neuroplasticity, the way that it can upregulate, downregulate genes to adapt to particular environments is absolutely incredible. And I mean, you can see for yourself after just a few weeks, astronauts who go to space are just flying around like Superman on the International Space Station. They barely know that they're in microgravity anymore, so they've adapted. But the problem is the gravity transitions when they come back home or when they land on Mars. It's going back and transitioning again back to that other environment where you've got to go from microgravity to normal gravity, and suddenly you don't have those reflexes anymore. So the question is, how do we maintain them? How do we keep those reflexes primed, ready to go? On Earth, you've got a lovely welcoming committee to carry you off to a reconditioning facility and build you up again, build your strength up again. That doesn't happen on Mars if we're going to Mars eventually. Bones and muscles waste away, so your bones get thinner, calcium comes out of your bones, muscles don't get used. You don't need your anti-gravity muscles when there is no gravity, so they kind of waste away. So exercise routines are really important. The suits that we've been working on, we call them intravehicular activity suits, are meant to gravity load the body in sort of an artificial way, trick the body's reflexes into thinking that gravity is still acting in an attempt to try and maintain bone strength, maintain muscle and balance and posture reflexes. And we're also working on some suits to try and protect your cardiovascular reflexes when you come back to normal gravity, kind of like a G suit that fighter pilots wear to keep blood pressure up when they pull G. When astronauts come home, they're essentially pulling G, but it's only 1G, but their reflexes aren't so good. So we're developing suits to help protect them. So it's those sort of things that we need to protect them against, and that's just gravity. I mean, then we've got to think about radiation, which is unlike anything we see on Earth when we go to space. The galactic cosmic radiation, the solar particle radiation that astronauts will be subjected to. We are protected on Earth in this sort of, we're almost like in our own little concrete bunker of atmosphere and magnetic fields. We don't get any of that radiation coming through to us on Earth. In space, we have to try and figure out ways to protect astronauts from that. And I think another big question, another potential showstopper is just human psychology. How do we deal with deep space missions when we are that far from home with no possibility of return? At furthest approach, Mars is 400 million kilometers away. You can't just turn a spaceship around and come home if there's a problem. You're kind of stuck. So I think one of the big issues is how do we support psychology and how do we give astronauts the autonomy they need to actually deal with any contingency that might arise? That's a real challenge, trying to predict what might happen and provide them with the resources in a very resource-limited environment. That's I think only partially answering your question, but it gives you a flavour for the sort of issues we're facing.
Look, I know that's super helpful in itself, and I find that really interesting. The point at the start too that the human body adapts to its environment. So I guess if standalone you were in a new environment that didn't have a great deal of gravity and all the other kind of radiation elements, not like the human body can't evolve into that particular scenario, but it's the moving from one state to another that's where that transition piece really kind of takes its toll. It sounds like a really dramatic jet lag to me in a very layman's interpretation, but much more physiologically too. And thinking that the role that Australia plays in all of that, because in this episode speaking to a lot of people around the world doing some interesting innovative stuff around humans in space and healthcare, what role is Australia playing in that landscape?
Yeah, look, I mean, we've got amazing medical research capability in Australia, I'm sure, as most of your listeners know. And when I was working for a little time there with the Space Agency, I was just really looking around Australia to see, what we were doing and how we were collaborating, if we were at all, what our potential sort of advantages were, market advantages were, and the technologies that we were developing that we could feed into space supply chains and pipelines to really use our technology in international missions and collaborate with international agencies. It was fascinating to see what people were doing. But, a lot of the the different research organizations, universities, companies that I approached, they were doing this amazing work. Sometimes they weren't even really aware of the space applicability of what they were doing. So when you said, oh, had you thought about, using that in space, or taking it to space, or further developing it in space, or the Earth-based applications of a space technology that, might be relevant, it actually really opened their eyes, and suddenly they thought, oh yeah, well, that's a potential thing that we could do. So I think a lot of it is, raising awareness in the health and biomedical research communities in Australia that the work they're doing could either be beneficial to astronauts going to space, could be better developed by using space as a laboratory, and that might then improve the product to bring back to Earth and actually have an even bigger market. So I think there's a lot to be thought of in that sense of using space, by developing technology for space to help us explore. That's true, but that's a very small market. The idea is to spin back. And so many technologies over the decades have been developed in that way. I mean, if you just look at the telemedicine technologies that have been used, from the ISS to Earth and on space missions to Earth, we now use telemedicine routinely on Earth. Even the good old infrared thermometer that we use in ears to take, a body temperature, that was originally developed from space technology, looking at infrared scanning technology, looking, from astronomy and from space, using that technology to read temperature on a human body. So there's been a range of things. Some of the things that are being currently looked at in space are things like development of pharmaceuticals. Protein crystals, because of the lack of gravity, grow in a much more structured, ordered way and could grow much bigger. And, proteins in the body, such as insulin, for example, can be grown in microgravity in a way that you just can't do on Earth. And in fact, some novel pharmaceuticals can probably be developed in that way as well. So I think, what we can do in Australia is use our amazing research brainpower to come up with ways to effectively use space to collaborate with international agencies. And of course, now commercial space is a thing. It's probably a little bit easier to get access to space, albeit still very, very expensive. Whilst we have to use chemical rockets to get off the planet and overcome that gravity well, it's always going to be an expensive exercise. But I think just to keep that thought going for a moment, the future of low Earth orbit will be commercial space stations. And companies such as Axiom are already planning for that. They're already building modules that will be attached to the International Space Station so that when the ISS is eventually decommissioned, there'll be an Axiom private space station, space laboratory still in orbit, and there are other companies looking at similar ventures. So the future of on-orbit research, on-orbit manufacturing, I think, is just going to grow.
And we're lastly thinking about then, I guess, the practicality of it's great hearing some of those examples of things that we just take for granted now in terms of, like the infrared thermometer that you brought up, or the, I guess, telehealth too. And I'm sure there's other examples. And it is interesting hearing about utilizing a space environment, almost like an incubation space for pharmaceuticals. So that's super cool. Where do you see, practically, in our generation, is this an area that people should be watching just out of interest, or is there more practical day to day that I guess space travel is going to apply in healthcare more broadly, or is it more of a watch this space and let's hope the future generations kind of do something cool with it?
Yeah, look, I think anybody interested in healthcare and novel research and novel developments in space should be watching the space environment, because I think there's going to be a number of technologies spin out of that, assuming we do continue our push to explore deep space. Of course, international space organizations, whether you're talking Europe, whether you're talking the US, they have plans, but they can spin on a dime essentially and change their mind suddenly. If funding is removed, suddenly programs collapse. So let's assume that we are going back to the moon. Let's assume that plans for Mars will continue. I think the sort of developments that people need to watch will be those that improve the autonomy of crews in deep space, because your audience may not know, but the speed of light time from Mars at its furthest approach is 20 minutes. So if you want to communicate with somebody on a spacecraft in orbit around Mars, it's going to take 20 minutes to get the message there. And it's going to take another 20 minutes for the answer to come back. So real-time communications is just not going to work. So their autonomy will be important. How do we make them autonomous? I think we need to look at AI and robotic systems for healthcare. We need to look at how AI can support diagnostics based upon, for example, wearable biomonitoring equipment, which has already been in development for some time. But it's that sort of monitoring and the data analytics that goes along with that will be really important. The predictive analytics, I think, is going to be really important. We've been certainly looking at that in some organizations overseas in Canada that have been looking at data analytics that arose actually from the monitoring of neonates in intensive care units, so neonatal intensive care units, looking at how AI could analytically predict the deterioration of parameters and the deterioration of a little patient before it actually happens, so interventions could be instituted. And that technology has already been rolled out to crews working in extreme environments on Earth, in fact. So that sort of AI is what astronauts are going to need. Robotics, in terms of robotic surgery, might be something to look at. But the other thing is making things as you need them. How can additive manufacturing, 3D printing, assist in the creation of the tools that you need? Because you just can't take everything with you, and you've got to have the ability to make stuff that you need at the time that you need it. The weight, mass, volume problem of space is never going to go away, and we need to be able to make the stuff that we need to solve the problem that's at hand, or we need to be able to make the pharmaceuticals or the nutrients, the macro or micronutrients that we need. So I think the other space to watch is synthetic biology. How is synth bio going to help the creation of molecules that are needed at the time to treat certain problems by having essentially switchable biofactories on spacecraft or on habitats, whether that be the moon or Mars, because there is no resupply. There is no getting stuff there, and pre-deployment of stuff isn't necessarily going to be ideal either. As I don't know whether your listeners are aware, but Mars, to get to Mars, there is a 2-yearly launch window. To get crews to Mars, it is inevitable we are going to have to launch support materials probably 2 years before the crew actually launch themselves. So if you want to send pharmaceuticals or medical supplies, pre-deploy them to the surface of Mars ready for the crew to arrive, they have to be hardy enough to survive 2 years in that Martian environment, and they may not be effective once the crew gets there. So making it at the time by the crew themselves when they need it is probably going to be a better solution. So I think they're the technologies to watch in the future.
And so if I was thinking then, this all sounds really great, but my deep question all kind of comes back to why are we even looking at going into space? I mean, we've got problems to solve here on Earth, and it sounds cool and all, but what are the reasons why we would want to go into space?
I guess I would answer that in two ways. Firstly, economic, and then a little bit more existential. I think economically, most of the studies that have been done on return on investment have shown that for every dollar spent in space on medical or healthcare research, it spins back multiple times to Earth. I think it's like 9 to 1 or something like that I've read in published papers. So for every dollar spent in space, there's $9 benefit. I mean, it's not just in the marketing of the material that you build, but it's the saving of healthcare costs, the prevention of disease, the prevention of death, prevention of, or reducing days in hospital, all those kind of economic advantages that have to be factored into those technologies that can improve healthcare. So that's my first answer, economic. Secondly, existential. I mean, exploration for humans is in our DNA. We need to go. I don't think sending robots is the way to do it. I mean, for a start, humans can think much faster and do a lot more productive work and much more quickly than a robot controlled remotely from Earth. So I think, us being on the ground to be able to actually do stuff quickly, we'll get a lot more answers. But we need to go to solve the big questions of life. Is there life out there? Are we the only life? Are we going to find bacterial life in the water that's been found on Mars, which will open up a whole new realm of biology? We need to understand the geology and the origins of the early solar system, the inner solar system. So that's really important. But I think the other existential point I would make is I think we learn a lot more about ourselves by just looking back at ourselves from space. I think the iconic Apollo 8 photograph of Earthrise, the first time we actually really saw Earth from space, saw that is all of humanity right there in that one photo, with the exception of the astronauts that took it. That is existentially changing. And I think probably we need to do that from time to time. We need to be a little bit reflective of ourselves as a species and look at our lifeboat of Earth being lost in this huge black cosmos and say, gee, that's all of us. I think that really puts it into perspective. I think going to space gives us a perspective of ourselves. So that's the existential answer to that question.
So I'm Lisa Brown, and I'm a New Zealand-trained hepatobiliary surgeon, but I'm now relocated and I'm living and working in Australia in Melbourne at the Royal Melbourne Hospital and Peter MacCallum Cancer Centre. And so the bulk of my work is day-to-day, surgery and operating and doing acute call. But since I was at medical school, I've done concurrent research and training courses in space medicine. And that's always been kind of my high skies kind of fun things that I do.
Yeah.
And yeah, so I've always been interested in astrophysics, and that's, I think, where it all came from. And back from starting at medical school, in my summer holidays, came over to Australia from New Zealand and learned about aviation medicine from Professor David Newman, who's also based in Melbourne and is a world leader in aviation and space medicine. And then I took time out from my surgical training to do a PhD. And whilst I was doing that, which was in surgery, I took up some astrophysics papers at university to kind of learn more about the interest that I had there. And then from there, things kind of spiraled. So I went...
At that point, it spiraled? Or
I kind of went to the University of Oxford after my PhD and was the Space Medicine Research Fellow. And I was looking at how you could use low oxygen, so make people hypoxia, to make them fitter for surgery. So we often we use prehabilitation programs for people, particularly sort of more elderly people, to get them fitter for surgery, to get their cardiovascular and respiratory fitness up. But what if someone has, significant arthritis or hip problems and they can't do that exercise program? So we utilised in Limerick, Ireland, at the University of Limerick, which is a big sports university, and they have a house where you can regulate the oxygen levels. So you pump nitrogen in to displace the oxygen. And basically people were living there for a week at the same level of oxygen that we regularly exposed to an aircraft cabin, like in a commercial plane. And I performed cardiopulmonary exercise testing to check their level of fitness during they had a week at hypoxia, a week at normoxia, and assess the level. So that was really interesting. And we definitely found a trend of improvement, but nothing absolutely formalized, but that was great. And then after that, I came back and finished my surgical training. But I also went to Houston, to the University of Texas Medical Branch, who run a short course in space medicine, which people from outside of the US can attend. And I got this scholarship to attend that, and I was the first New Zealander to go, and the first Australian to go was also there at the same time as me. And so we got to spend 5 weeks in Houston and spent time at Johnson Space Center in the Neutral Buoyancy Laboratory and meeting astronauts and learning all about space medicine, which was fantastic. I then also went to Cologne, Germany, and I did a internship with DLR, which is the German Aerospace Center, which is situated at the European Astronaut Center in Cologne, in commercial space flight and health. And then I've just continued research with international partners and sat on different governing bodies and committees for space. And then I helped set up the Space Surgery Association, which is a big international group. And we've got hundreds of members around the world, mainly surgeons, but it's important to include all facets of surgery. So, anesthesia, physiotherapy, everything around it. And I set up the New Zealand Space Health Research Network, which is a national conglomerate trying to pull all researchers together from across New Zealand to sort of try and support everyone, but through the experiences that I've had, to help them, get international collaborations and try and help people to see that the work that they're doing in health or health tech can be translated to the space environment and vice versa. And due to the rapid kind of advancement that we get in space technology, we can utilize that rapid advancement to try and help healthcare healthcare on Earth.
Yeah.
So, yeah.
That's a super fascinating background. We could dive into any of that, but the two things come to mind. Firstly, what I'm kind of learning through this process is there seems to be a lot of interest, or there seems to be an opportunity to look at, to kind of take the big picture view and look at, we're currently doing things in healthcare right now on a day-to-day on Earth in this particular way, and everyone's researching and exploring ways to do things better or in a different process, and hopefully that improves patient outcomes or efficiency or efficacy, or however we want to measure it. But there's almost this opportunity to leapfrog or think differently around some of these problems, because if you can take there's that saying, constraint drives creativity. So when you've got like reduced kind of environments, or you've only got a certain kind of set of tools or things available to you, then it almost makes you think differently about solving problems. And then hopefully you can take some of those learnings and apply it back on Earth. Is that one of the main things? Because originally when I was going into some of these conversations, I think of, we're talking about space health because humans might be in space more soon and need to do healthcare on them. So I'd love your take on some of that.
Yeah. So I think space medicine, space health is thinking about the way that the space environment affects the body, which is mainly through things like microgravity, radiation, the isolation and the distance from Earth and from a tertiary center, and then how we can mitigate like all those effects. And I think, in this day and age, we've got limited funds, and particularly like, obviously I live and work in Australia, but I'm very familiar with New Zealand, and New Zealand has got, got limited money for the healthcare system and is going through, struggles with that at the moment. And so I could absolutely almost feel people listening to the podcast and thinking, why the hell would you be putting money into space medicine when we can't even solve problems in our current hospitals? And I 100% hear that. And I think that's, really important. So I guess the thing that I've always found exciting about space medicine, though, is that there's been a huge amount of translational things. So when astronauts first started going to space, because of the lack of gravity, our fluid and blood pulls differently in our bodies. Instead of pulling down towards our feet from gravity, it gets redistributed around our body. And it changes the way that our heart pumps because of these kind of things. And they were finding that a lot of astronauts in essentially a cardiomyopathy, which we see in, patients on Earth develop cardiomyopathy for various reasons. And actually through the targeted investigation and the mitigation of these effects, because it had to happen so rapidly because the space program was advancing so fast. And all of that is now being applied back to cardiomyopathy on Earth. And so, we've learned from the space environment things that we might not have learned for many decades on Earth, but because of that rapid, uptake, that's helped. I think that the technology that we use in space, from things like satellites, can have, again, it's just such a leap in advancement that we can use it. So continuous glucose monitoring devices that people wear on their arms for diabetes, that's all come from space satellite technology. That's where that came from. Another interesting example that I actually saw just published recently was about technology that was used to enhance imaging from things like the Hubble Space Telescope, has now been used to help enhancing imaging in mammogram detection for breast cancer. So all these things, can be applied back, and I think that's really exciting. Just the actual environment of in space and microgravity, also for laboratory type experiments in terms of health, can be used because cells act differently in space. So when astronauts are on the space station, they're predominantly doing research experiments all day, for multiple days in the day cycle. And some of that is involved testing like different chemotherapy agents on cancer cell lines that they can see the effects speeded up in the microgravity environment. So it's enabling us to get more information quicker to be able to advance that technology back on Earth. So yeah, like I said, I appreciate, people think, why are you looking at this? But there are so many benefits to health on Earth, and that's really, really, really important.
Yeah. Look, I was thinking earlier when you talked about the bringing together or the network of surgeons and space specifically, I wouldn't have pictured. I would think the logistics of doing surgery in space would be kind of tricky, but I based on some of those examples, that's I can see how some of the tools and the approaches and things could be really useful. And I guess and to the other point that you raised around the sense of urgency that was created around some of the, let's get this capability up because, there's a deadline. I guess the scenario we're all familiar with over the past couple of years when we look at the rapid utilization of virtual care and the all of the frameworks and things that exist around it because it needed to during the pandemic. So I can see the correlation between, and that it's almost a separate call out around sometimes innovation needs that sense of urgency or the burning platform in order for stuff to happen, because when we've got that, we can really see some transformational stuff. But then when there's not the priority or there's competing funds, we can be in that environment. We're so often in healthcare where it just feels like there's a bit of stagnation. So that's interesting in and of itself. And so the work you're doing now and still reflecting on in terms of space medicine and space and healthcare, what's exciting you, and what are you looking at with interest? And can you give us a glimpse into what we may see next over the coming months and years?
So I guess two main projects that I'm really passionate about is, obviously I'm a pancreas and liver surgeon, and so I'm really interested in about the liver in the microgravity environment, and particularly as it relates to changes in the liver itself in terms of developing what we call non-alcoholic steatohepatitis, which is where you get changes in the liver which could eventually progress to things like cirrhosis and worst case HCC, hepatocellular carcinoma. And from experiments done in cell studies and hepatocytes, and as well as rat and mice experiments, which other groups have taken to the space station, have found that those kind of changes are seen in the liver in the microgravity environment because of the microgravity, but then also coupled with the radiation exposure from background cosmic radiation. And so, the worry would be, if you're on a extended duration mission to Mars, are you going to be exposed to this, that you then come back to Earth and develop cirrhosis and HCC? So trying to understand the pathways and how that interacts is something really interesting. And the other part of the liver is gallstones, which is super common. The commonest operation general surgeons do now is cholecystectomy, and a lot of the bile flow that we see is because of gravity. The biliary tree doesn't have cilia, it doesn't have valves. It's all just dependent on sort of gravity coming out of the intrahepatic bile ducts down the bile duct into the duodenum. And so when you're in space, you don't have that. And so there's increased risk of things like crystallization of bile and development of gallstones. So we're undertaking a big project through the group in New Zealand, led by me and Professor Anthony Phillips from University of Auckland, who's the other lead of the Space Health Research Network in New Zealand, looking at protein crystallization in gallstones and microgravity. And the main driver for me for that project is figuring out how gallstones are formed with a better understanding, and then how can we target it to stop it forming? Because if we can do that with something as simple as a medication that can be used for astronauts, but then can be used on Earth, I mean, imagine that. It'll be incredible. So that's something, I'm really excited about. And then the other project that I've been looking at through with the University of Melbourne, with my position in Melbourne, with a medical student who's going to be a bright star, Dr. Cameron Shetler, and we've been looking at melanoma. And, we have such high incidences of melanoma in New Zealand and Australia, like the highest in the world. But also astronauts also have a high rate of melanoma and non-melanomatous skin cancers like SCC because of that radiation exposure. So we're trying to figure out the different links, and, Peter MacCallum Cancer Centre in Australia is a world leader in melanoma research and treatment. So we're starting to figure out ways that we can get involved with the researchers there to figure out ways, particularly in space, that we can manage that and then back to Earth, that translation.
We hope you enjoyed this episode of Talking Health Tech. Make sure you like and subscribe and share this episode with someone who might find it valuable. For more information and resources about healthcare innovation, visit talkinghealthtech.com.